All right, so this is example 6.2 from the lecture slides, and we got the schematic right here, and the given equations of motion are right here, and you're tasked with obtaining the state space model with P as an output. So step one is pretty similar to everything we've done so far. You just want to get inputs and outputs. In this case, it told us that the input was U and that the outputs, it didn't tell us that, but we could tell that they're PQ by looking at either the schematic or the equations of motion. If you look at the schematic, this big line with the arrow coming out of it with P denotes that this is an output. Big line arrow coming out of it, Q, must be an output. And then the arrow coming straight from one of the boxes, if it's directly applied to one of the masses, that would be your input. So inputs U, outputs PQ. You also need to write system order. In this case, the system order is 4 because we have 2 second order differential equations. How do we know they're second order? We look at the highest derivative that's in them. So we see P double dot is a second derivative, second order. Q double dot is second order. So 2 second order equations, you sum that together and you get 4. State variables, this is always going to match your system order. So if your system order is 4, then state variables would be 4. And what I would do then is go ahead and list what your state variables are going to be called. So I said x1, x2, x3, and x4. So that would be step 1. Input, output, system order, and your state variable number, or like number of state variables, and then go ahead and list them out. Step 2 is rearranging the equations of motion. So all that means in this case is just isolating your P double dot and Q double dot, or whatever letter double dot, you just want to isolate that. So from the first equation, all we did was move everything over on to the other side of the equal sign, and then we divided by M1. So we moved everything over, and then we divided by M1 to isolate P dot, or P double dot. We did the same thing with Q double dot, moved everything over, and then we divided by M2. And that gave us this. And so now you isolated both of them. And so you're done with step 2. Step 3, the very first thing you want to do is define your state variables. So remember, I said x1, x2, x3, and x4. You want to go ahead and say, okay, x1 is equal to P, x2 is equal to Q, and then x3 we'll say is P dot, and x4 is Q dot. Just make sure you're going in order. After you define your state variables, you have to take the derivative of them just once. So that would mean your x1 dot is equal to P dot, which is also equal to x3 from earlier. X2 dot would be Q dot, which is also equal to x4 from earlier. X3 dot must be P double dot, and x4 dot must be Q double dot. After you define your state variables and you take their derivative once, then you just want to rewrite the equations of motion that you rearranged earlier. So your rearranged one, you just want to rewrite them and replace any of those variables with your state variables. So for example, x3 dot we said was P double dot. So we rewrite this whole equation using that stuff. So x3 dot equals 1 over m1u plus k1 over m1 x2. Because if you look at the original, we had k1 over m1q, which is represented by x2, and then that, and then that, and then that, and that. So yeah, that up until this point, everything is pretty easy. So inputs, outputs, system order, state variables, rearrange the equation, define your state variables, take their derivative once, and then go ahead and replace the original outputs or the original variables with the state variables that you just defined. Now, the fun part is making the matrix. So making the matrix is actually pretty easy and not as mind-bending as you think. There's just a couple of things that you need to remember. So the first thing in the matrix, also bear with me if this isn't like clear, if it doesn't focus. I'm going to take the camera off so you can see it all while I'm writing, but it might be wonky at first. But anyway, the very first thing is in every state space model, the very first matrix is just going to be all of your state variables dotted. So we have x1 dot, x2 dot, x3 dot, and x4 dot. So that's the very first matrix. And then all of that is going to equal that big, scary, disgusting, ugly looking confusing looking matrix, right? So it's actually not that bad. In this case, we said we had a system order of 4 with 4 state variables, right? So if we have 4 state variables, that means our matrix needs to be a 4 by 4. So go ahead and write at the top what the different columns are. So we have x1, x2, x3, and x4. Now, filling it out is not bad at all. You just need to understand that the first half, the upper half, only refers to that state variable's order in the respective equation, and the second half refers to what their coefficient is in that equation. And I'll show you what that looks like right now. So let's start with the x1 column first. The very first thing in the x1 column would be, what is the order of x1 in the first equation of motion? So we go back to the equations that we just wrote, right? And we look for x1. We see we have x1 right here. Do we have an x1 dot? No, all we got is x1. And that's no derivative of x1, just x1. So the order of x1 in the first equation is 0. This second space is the order of x1 in the next equation. Okay, so we go to the second equation. What is x? Do we see x1? We see x1. Do we have an x1 dot? No, there's no x1 dot, which is just x1. So the order of x1 in the second equation must be 0. Now, these first two rows concern themselves with the order in the respective equations. This is first equation, this is second equation. After that, it goes to coefficients. Okay, we go x1. What's the coefficient of x1 in the first equation? So we go back to our rewritten first equation. Where's x1? We see x1 right here. What's the coefficient? Negative k1 over m1. Negative k1 over m1. Okay, and then the second spot refers to the coefficient in the second equation. Okay, so here's the second equation. We need to find x1. Here's x1. What's the coefficient? K1 over m2. K1 over m2. And then the same thing for x2. What's the order of x2 in that first rewritten equation? We see x2 right here. Do we see a x2 dot? No, all we see is x2. So the order in the first equation must be 0. What about the second equation? Is there a x2 dot? No, it's just x2. So the order must also be 0. And then going back again, we did the orders. Now we need to do the coefficients, which is the second half of the matrix. So what's the coefficient of x2 in the first equation? We see k1, m1. So we go k1, m1. What's the coefficient of x2 in the second equation? We see, where's x2? Right here. Boom. Negative k1 plus k2 all over m2. So we see negative k1 plus k2 all over m2. Same thing for x3. We go to the first equation. What is the order of x3 in the first equation? Well, we see x3. Do we see a x3 dot anywhere in here? Yes, we do. We see x3 dot. It's just one dot. So the order in the first equation for x3 must be 1. Now, what about the order in the second equation? Do we see x3 in here? Yes, we do. Do we see x3 dot anywhere in here? No, we don't. So 0. What's the coefficient for x3 in the first equation? Where is x3? Boom, right here. Negative b1 over m1. Negative b1 over m1. What's the coefficient of x3 in the second equation? X3 is right here. b1 over m2. b1 over m2. Now we go to x4. What's the order in the first equation? Do we see a x4? Yes, we do. Do we see x4 dot anywhere in that? Nope. So that must be 0. What's the order of x4 in the second equation? We go to our second equation. Do we see x4 dot anywhere in here? We do. We see 1 dot. So x4, the order of it in that second equation must be 1. Same thing with the coefficients. Coefficient of x4 in the first equation, we see b1, m1. b1 over m1. coefficient of x4 in the second equation, we see negative b1 plus b2 all over m2. Negative b1 plus b2 all over m2. And then you've completed the ugly, big, disgusting matrix, right? The next thing that comes next, or like the next thing is just a single, like, one column matrix with all your state variables listed out, but this time no dot. So we had all the state variables dot equals that big ugly stuff plus all your state, or times all your state variables in their own matrix, right? And then we need to do the last one, which would be for your input. So go ahead and create the matrix for your input. In this case, our input is U. Okay, so this works the same way as this matrix. The first half refers to the order in those equations. The second half refers to its coefficients. So we see, what's the order of U in the first equation? Let's see, is there a U in here? We do. Is there a U dot? Nah, so it must be 0. Now, what's the order of U in the second equation? All right, do we see a U in here? We don't even see a U in here. So there's nothing there. You just write a 0. Okay, now what's the coefficient of U in the first equation? We go to the first equation, we see, oh, there's a 1 over m1. So we write 1 over m1. What's the coefficient of U in the second equation? And nothing, because we don't even got a U in that equation. So we just say 0. And that completes that matrix. And you want to do all that times U. So to go over this again, all you really need to remember is this. First, make a little matrix, one column with all your state variables dotted. So x1 through x4 dot. That must equal the big ugly matrix with all your state variables in their own column. The first half of that matrix just refers to the order in the equation. So this first row is what is the order of that state variable in the first equation. And you get that from your equations. Now, what's the order of that state variable in the second equation? You get that from the equations. And then you get to the second half of the matrix down here. What is the coefficient in the first equation? What's the coefficient in the second equation? And then you fill out that big ugly matrix. And then the next one, which is multiplied with the big ugly matrix, is literally just one column of all your state variables. This is always going to be that. And then you do plus a one column matrix that represents your input. So again, order of the input in first equation, order in second equation, and then coefficient in first equation, coefficient in second equation. And this would be like your whole completed state space model. But it asks us to obtain the state space model with P as an output. So that's really easy. So to represent P as the output, I already did it right here, but ignore that. I'm gonna show you how to do it. All you gotta do is say Y equals a matrix. It's gonna be one row, and we're concerned with P, right? What did we say P was represented by earlier? We said P was represented by x1. So in the position where there is x1 for P, you write 1. And then everything else is 0, 0, 0. Boom. And then you follow it up with a little matrix of all your state variables like this. So this whole thing would be your state space model, and this is representing P as an output.